Okay, today's lesson is going to continue on with solving for KEQ, but the difference today is that we're going to do this using experimental data. So we're going to call these ICE problems. The I, C, and E are going to stand for initial, changing, and equilibrium. And we're going to learn how to make an ICE table to solve these types of problems. Okay, so this is the set of steps that you need to follow to solve these types of problems. As opposed to reading each step, it would be easier if we just jump into an example and follow the steps as we go. Okay, so here's a type of problem that we could come across that would be solved using an ICE table. So this tells us we have 2 moles of NO2 and that's injected into a 1 liter flask. At equilibrium, the N2O4 concentration is 0.64 moles per liter. What is KEQ for this reaction? Okay, the reaction is shown below. We know it's a reversible reaction because of the arrow. Okay, and now previously when we would solve a KEQ problem, we would always know, we'd write out our KEQ formula, and we'd always know what the concentrations of the products and the reactants were at equilibrium. But right now, we don't know that. All we know is the equilibrium concentration of the N2O4, and then we know the starting amount in moles and volume in liters of the NO2. Okay, so we've been provided with some different information. So what we can do with that, to calculate KEQ for a reaction, we need to know what those equilibrium concentrations are. Okay, so we have to figure out what the equilibrium concentration of the NO2 is. And right now we don't know that. Okay, for the reaction above, the equation tells us that for every mole of N2O4 that forms, 2 moles of NO2 react. And I'm getting that simply by looking at the coefficients in the balanced equation. So this mole ratio is going to be something that becomes important when we solve these types of problems. The equation does not tell us the relative amounts of these chemicals present at equilibrium. Okay, but we can use the mole ratio of reactant and products to predict the equilibrium concentrations of the chemicals and determine the value of KEQ. So in the problem above, we're going to use an ICE table to calculate the equilibrium concentrations of reactants and products, and from there we can then calculate KEQ. So let's solve this problem. So our first step is going to be work out any concentrations we don't yet know. Okay, so we are told the concentration at equilibrium for the N2O4. But for NO2, we're being told the initial concentrate, or not even the initial concentration, but the initial amount and the initial volume. But from that, we can calculate the initial concentration of the NO2. So let's write that. Initial concentration of NO2. And we know that concentration can be solved using C equals N over V. Okay, so N divided by V. So I know that there are 2 moles and 1 liter. So therefore, the initial concentration is 2 moles per liter. Okay, so I'm going to make a table like this, and it's called an ICE table because I need to identify 3 things represented by the letters I, C, and E. The initial concentrations of all reactants and products, their change in concentration of all reactants and products, and the equilibrium concentration. Okay, so let's work our way through this table one thing at a time as we know what these values are. So we just found out that the initial concentration of the NO2 is 2 moles per liter. So that's already been entered in the table for you. Okay, now we're always going to assume, whether we're told, unless we're told differently, that the initial concentration of the product is 0. Okay, so before the reaction has taken place, right at the very beginning, no products have formed yet because the reaction hasn't taken place. So there's a 0 concentration of the product to start with, and the reactant has this concentration, and we know that from our calculation up here. Okay, the other piece of information that we know is this 0.64 mole per liter is the equilibrium concentration of the product, N2O4. So that is entered in the table. So how do we fill in these 3 missing spots? This change in concentration is going to be the key to figuring out the rest of the table. So how did the concentration of the N2O4 change? Well, it went from 0 to 0.64. So what happened was it simply went up by 0.64 in order to get from 0 to this value here. Okay, so that's pretty easy to figure out. Something to pay attention to is your products are always going to have a positive change in concentration because they start off at a concentration of 0, and as the reaction progresses and more reactants are used up, more and more product forms, which increases its concentration. So you're always going to have a positive change here. For the NO2, the reactant, the opposite is true. The reactant concentration is going to decrease as the reaction progresses because the reactants are going to get used up more and more as time goes on. So this is always going to be a negative change here. Okay, so we'll look at that in our next step. Okay, so step 3 was determine the change needed to get to the equilibrium concentration for the chemical you know the equilibrium concentration for. So that's what I just did there. In order to get from 0 to 0.64, we have to add 0.64. Okay, so how can that be applied to our reactant? So we're going to use the mole ratio to determine the change in concentration of any other chemicals involved. So I know that the change in concentration of N2O4 is 0.64. Okay, so let's use our mole ratio. So I want to cancel N2O4. So I'm going to put it on the bottom because that's what I'm currently in here. And I want to get to NO2. So I'm going to put that on the top. If I look at the balanced equation, I'll just scroll up for a second. Okay, so looking at our balanced chemical equation, we can see our coefficients here, and that's our mole ratio. So we're going to put in a 2 here and a 1 here. Okay, so all this is doing is just showing the change in relationship to one another. And that's simply based on how many moles of each reactant and product you have. Okay, so N2O4 will cancel. 0.64 times 2 is 1.28. Okay, and that's going to be the change in concentration of the NO2. Now remember I said that as the reaction progresses, the concentration of the reactants decreases as they get used up. So I'm going to add a negative sign here. Okay, so let's just put a little note about that negative sign. Okay, reactants will always have a negative change in concentration. And let's just put a note up here. Products is the opposite. Products will always have a positive change in concentration. Okay, so now that I know this, I'm going to fill that negative 1.28 into my ICE table. Okay, so I'm just kind of adding to this ice table as I go. So step 5 is to work out the equilibrium concentration. So there is only one equilibrium concentration I need to work out, and that's this one here. So all I do is 2 subtract 1.28 to get that value. Okay, so I'm just going to go 2 subtract 1.28 equals 0.72. So that means that the equilibrium concentration of the NO2 is 0.72 moles per liter. So I use this ice table to get to this value here, because without this value, I can't solve for KEQ. Now that I have both equilibrium concentrations, I can now solve for KEQ. So let's go on to the next page and do that. So to solve for KEQ, I'm going to set up just like I've done before. Products on the top. So the concentration of N2O4, there's no exponent because there's no coefficient, divided by the concentration of the NO2, and that's going to be squared because of the coefficient 2. Now I just simply plug in the equilibrium concentrations. This is the one I was told in the question, and this is the one I just figured out using the ice table. After that, it's just some simple calculation to get to the answer of 1.23 for our value of KEQ. Okay, so equilibrium concentrations, you've already stated those in your ice table, but just to state them again, the concentration of N2O4 at equilibrium was the 0.64 mole per liter, and the concentration of NO2 at equilibrium was the 0.72. Okay, so let's just do a couple more examples until you get the hang of it. So we've got an experiment, and it started off with a mixture consisting of 0.5 mole per liter N2, 0.8 mole per liter H2, and it was allowed to reach equilibrium. The chemist found that at equilibrium, the concentration of NH3 was 0.15 moles per liter. Calculate the equilibrium constant. Okay, so here's our reaction. Let's fill in as much as we know at this point. So a chemist started an experiment. So that's telling us at the beginning, our initial concentrations, we know that N2 is 0.500, H2 is 0.800, and because the NH3 is the product, we assume its concentration is 0. The other piece of information that we know is that at equilibrium, NH3 has a concentration of 0.150. Okay, so from here, we have enough information to calculate all the rest of these values and then calculate our KEQ. So here we can see very simply that to go from 0 to 0.15, it's a positive change of 0.150. So let's use that to help us fill in the rest of the chart. So let's say the change in concentration of NH3 is 0.150, and we're going to use our mole ratio. So I'm going to put NH3 on the bottom, and I'm going to start with H2. I'll put H2 on the top. In my balanced equation, I have a 3 here and a 2 here. Okay, so if I multiply 0.15 by 3 and then divide by 2, I get 0.225. Because H2 is a reactant, that's going to be a negative change. So I'm going to put subtract 0.225 here. Now I'm going to do the same thing for my other reactant. Okay, so I know I'm using this change in concentration, 0.150, and I'm just going to multiply by the mole ratio. NH3 on the bottom, and this time N2 on the top. N2 has no coefficient, NH3 has a 2. Okay, so I'm just dividing 0.15 by 2 to get 0.075. And again, because it's a reactant, that's a negative change or a decrease in concentration. Okay, so now all I have to do is subtract this value from the initial concentration and subtract this value from this initial concentration. So this subtraction would equal 0.425 and this subtraction would equal 0.575. Now I can go and solve for KEQ. So I've got my product concentration on the top, NH3 squared, divided by the concentration of N2 multiplied by the concentration of H2 cubed. So let's plug in those values. So I'm using the bottom line of my ICE table, the equilibrium concentrations, 0.150 squared, and then we've got 0.425 times 0.575 cubed. Okay, so if we do all that calculating, what we get is 0.278 for my KEQ value. All right, one more, and then you can work on the assignment on your own. Okay, so problem 3. Let's fill in as much information as we know. So it says, in an experiment, 2 moles of NaCl were placed in a 1-liter flask, and the concentration of NO gas at equilibrium was 0.66 moles per liter. Calculate the equilibrium constant for the reaction below. So we weren't told the initial concentration, but we have enough information to find it. So we're going to use C equals N over V. We've got 2 moles and we've got 1 liter. So we've got 2 moles per liter. Okay, so we put that in for our initial concentration of our reactant. The other 2 are products, so they would start at 0. The equilibrium concentration that we're given is that of NO, and it's 0.66. So we can use that. So we've got a positive change of 0.66 to get between these points. So let's figure out how the rest of the table should be filled in. So the change in concentration of NO is 0.66 multiplied by the mole ratio. So I'm going to put NO on the bottom, and I'm going to start with NOCl on the top. And I've got a coefficient of 2 here, so 2 moles, and a coefficient of 2 here, so 2 moles of NO. So it's a 1-to-1 ratio. So it's not going to change that value at all. So that's going to stay as 0.66. But because it's a reactant, it's a negative change. So I'm going to put negative 0.66 there. And then I'm going to do the same here. So my 0.66 multiplied by the mole ratio. And for Cl2, there's no coefficients, so oops. And I just missed the word mole there. Okay, so 0.66 divided by 2 is 0.33. And because Cl2 is a product, that's a positive change. Okay, now all I have to do is do my additions and subtractions to get my equilibrium. Okay, so 2 minus 0.66 is 1.34, and 0 plus 0.33 is 0.33. So now all I have to do is use those equilibrium concentrations to solve for KEQ. So I've got NO, the concentration of NO squared, multiplied by the concentration of Cl2, divided by the concentration of NOCl, and that is squared. So if I plug in, NO is 0.66, Cl2 is 0.33, and then we divide by NOCl is 1.34, and that is squared. So when you calculate that all out, you get 0.08 for your KEQ. Okay, so work on the assignment that follows, and I'll post the answer key for that tomorrow.